in fact non. Right. So this goes without saying that KL divergence is in fact non-symmetric. So go ahead, take a minute, think about what will happen when we try to optimize for P with Q or Q with P.
What's the blue color?
So the blue curve, right, my bad for not mentioning, it's just corresponding to the Q here. Blue is what we would end up learning when we minimize the divergences. So the blue is the Q curve and the red is the P curve. In case you're wondering, you would need to sort of reason about what gets penalized in a KL divergence, or in what cases would the modeling procedure be penalized the most.
I go for the one on the right for number one.
Right. So you're saying the one right would go with P with Q or Q with P. So all three of them correspond to one of the optimizations.
I choose P with Q.
Right. So you're saying the first one goes with P with Q. Any reasoning for that?
I meant the one on the far right. Okay, maybe it's on my right.
Yeah, I see it. I see this one, right?
Yeah.
Yeah. So
By reason,
why would you say that?
because I think KO divergence penalizes distributions that are not alike. So it just seems to be getting larger as you move away from the center. I don't know. That was my guess.
Well, that's fair. That's fair. What about these two? Why would these two then appear for Q with P? Well, I guess before that, which of these three do you think is a good approximation, actually?
The one on the left.
The one on the left. So this one.
Yeah.
Okay, that's fair. That's fair. So the actual answer is very similar to what you said. It is the fact that the rightmost develops with P with Q, and the left two would both can possibly develop with Q with P. Now the reason is this distribution is bimodal, right? In the sense that it has two means from which the Gaussians originate. So there are two sort of sets of data which are merging, mixing together to make this distribution. So when you try to optimize for KL divergence with P with Q, essentially what it does is it tries to cover both modes. It wants to be non-zero wherever your underlying distribution is non-zero. So it tries to cover the whole distribution area. The other two, their goal is to, instead of trying to be non-zero where it is non-zero, they want to be maximized where the underlying distribution is maximized. And of course, in a Gaussian, the maximum probability density lies at the minimum, in the middle, right? At the mean of the distribution. So Q with P would try to cover the mean with its learned mean. Unfortunately, because there are multiple means and our learned distribution is not bimodal, we will not be able to cover both. Instead, it would just focus on one of them. And this is what's commonly known as mode collapse, which happens. But right, so this is not entirely relevant to what we're going to be doing today, just to sort of get you started. But KL divergence does pop up time and time and time again whenever we do generative modeling. So it's good to sort of understand how it's working. Right. So the background for today's lecture would involve, of course, generative models and discriminative models. It would involve autoencoders, the plain vanilla autoencoders, and it would of course involve some of the ideas behind variational autoencoders. Primarily, we would be wanting to remember what the reparameterization trick is and what is the evidence lower bound. So before we dive into sort of diffusion models and normalizing flows, does anybody major hanging questions about any of these topics? Cool. I would take that as a no. I'm glad we are all good to go. All right. So today we will actually be talking about sandcastles and more specifically, how to create a sandcastle. So anybody wants to tell me how a sandcastle is usually created? If you've gone to a beach, try to make. Okay, early morning. All right. So usually you would want to sort of take a bucket, fill it up with sand. Yep, you use a bucket, you fill it with sand. You start with a mold. That is great if you want to achieve sort of complex structures. But I would give you an alternative, right? To build a very, very great sandcastle, you start with a sandcastle, right? And then you destroy the sandcastle. Then you sort of remember how you destroyed the sandcastle. And if you remember how you did it, even approximately, you can then just reverse the process and you end up back at your sandcastle. Now, I think this is a great way to actually make a sandcastle. And the key idea here that we want to take throughout this lecture is once you know how to reconstruct sandcastles, you can some different piece of sand, slightly different input, apply the same process, and you end up with a slightly different sandcastle. Right? Although this doesn't directly apply to sandcastles, but humor me here. This sort of metaphor will be very easy to understand going forward. So we will be flirting with this idea of sandcastles a lot in the next two parts of this lecture, both in diffusion models and normalizing flows, but we will be doing it slightly differently each time. Okay, so with that and a bunch of sandy socks, we can go into part one, which is diffusion models. Before we are able to dive right in, we should recap what the evidence lower bound or Elbo is, right? So first of all, why do we use the evidence lower bound? That's because directly maximizing P of X in most of our latent variable variational inference models was very, very difficult. It either involves marginalizing over the entire latent space Z, which is supremely intractable for complex models, or you end up having to access the ground truth latent encoder, which of course we don't have. I mean, if we did, we wouldn't need to use sort of a learned encoder anyway, right? So, right, so we can't directly maximize PFX in these situations. So we use the evidence lower bound instead. What the evidence lower bound does is, as the name speaks, it sets a lower bound to the log likelihood of our data. And if we increase the lower bound, we are indirectly or directly sort of increasing the log likelihood itself, right? Now, a question is, why does the greater than equal sign sort of show up here? If you go through the derivation, which would be there in the appendix, mind you, the appendix would not be there in the slides I sent to the TAs yet, because I was still making edits still right before this lecture. I will send updated slides with the appendix and all the derivations in there. But that aside, if you go through the derivation to arrive at the evidence lower bound, you'll see that there is a KL divergence term, which shows up somewhere in there, right? And KL divergence terms are always greater than or equal to 0. And so once you drop that, you instead of sign blank here. Something that's interesting is that this KL divergence term is essentially trying to measure the distance between the true posterior for the latent encodings given our data and our learned encoder, which is parameterized by phi here, which is again z given x, right? So by maximizing our evidence lower bound, we are also in a way reducing this scale divergence and hence bringing the two closer, which is also part of our goal. Right, so once again, applying the chain rule of probabilities, this evidence lower bound breaks up into two terms, which one of them would correspond to the reconstruction, which is how well are we able to reconstruct our original data x from our latent z, and a prior matching term, which tries to bring our imposed posterior on the latent as close as possible to our assumed prior. Right. So maximizing the evidence lower bound means you maximize this reconstruction term and you minimize the prior matching term, which goes with what we wanted to do in the first place. Right. Once we are clear on Elbo, we can now go into variational autoencoders, give a brief recap. So essentially, we are going back and forth from our data dimension to our latent dimension. And we go from the data to the latent using a distribution Q, which is z given x. And we go back to the data using p x given z. And for variational autoencoders, we learn both of these, and they are parameterized by theta and phi here. And some of the key pointers in VAEs is that one, the latent variable is sampled from a normal distribution, which is centered around the output of our encoder, right? So the encoder is parameterized by phi, and we have our mean and our variance here. We employ the reparametrization trick, which is instead of sampling from the full Gaussian, we can instead say that, hey, our mean is the mu phi of x, our variance is now, or the standard deviation is now sigma phi of x times a noise term, which is then sampled from a standard Gaussian. The reason why this is done is, or let me throw this to the floor, given that Professor Biksha is on the call, I would like to see if somebody can answer, why do we need to use this reparametrization trick? Why would it not work without it? Any takers? Exactly. So the sampling process is not differentiable. And sorry, I have to apologize in before going any further. I have two cats running around the place. So the slides might go forward, go back. There might be no sharing of screen suddenly. But please, if that happens, bear with me. I will get them off the computer and get back to the lecture, which I'm having to do right now. But okay. So we do the reparametrization trick because the sampling process is not differentiable. And with this, we can sort of remove the sampling process from our backward pass, and we're able to train all the parameters. What's left is the training is done jointly. We optimize both things and store bound. Right. So for VAEs, empirically, researchers have found that two things make VAEs work really well. One, increasing the depth of the networks, several times going very, very, very deep. And second, introducing a hierarchy of latent variables. So there was this in one particular study I read that it's corresponding to Plato's cavemen. Essentially, they feel that lower dimensional things like 2D shadows and things are just projections of higher dimensional objects or 3D objects. In a similar way, here we say that X is not just defined by one latent Z here. In fact, on top of Z, there might be more latents which are defining how this latent is functioning, right? So once we introduce this hierarchy of latents, which sort of then looks like this sort of chain here, such that each latent is conditioned by all of the previous latents, we arrive at what's called as a hierarchical VAE or a ladder VAE, right? This is a misspelling here. It's not have, it's HVAE. And we are particularly interested in having an HVAE which possesses the Markovian property. Essentially, the entire process is a Markov chain, right? Before going any further, do people have questions about what is a Markov chain, or does somebody want to tell me what they believe is a Markov chain? Okay, so essentially, a Markov chain is nothing but a chain of events in which instead of having conditioning or reliance on all previous latents or all previous stages events, you only have reliance on the one that came just before. So if you imagine a DAG or a directed acyclic graph, you basically imagine that each node is only dependent on the node that comes before that, none of the others. Exactly. So only the previous state matters, right? So now instead of having a hierarchical VAE in which we need to remember the conditioning of all the previous latents, instead we reach a point where we only care about the latent which came right before. So visually, it would sort of end up looking like this. We have our data X and we have our first latent Z1, and then we have a bunch of latents which go beyond it all the way till Z capital T. So T is our sort of time step measuring variable here. And you'll notice that now we have our encoding process, which is defined by QZ given the input X here. Now goes from Z1 given X to Z2 given Z1 and all the way to ZT given ZT minus 1. And similarly, the generation process, which is going in the reverse direction here, goes from PZT given ZT plus 1, essentially, right? And you can see the Markovian property in action here because none of these variables are conditioned on anything other than what came right before them in that direction, right? So with this, we can now rewrite our joint probability and posterior probability like so, like a product of class conditionals, sorry, a product of posteriors along with this initial prior here. And for this posterior, we can once again write it as a product of individual posteriors. Why are we doing this? Because we need this to define our evidence lower bound. If you recall, the way we defined elbow before was with a joint probability here and a posterior probability here. So we can get back to it using the updated joint and posterior like so. So our expectation is now over Q5 for Z1 through T, so which is all of the higher degree latents given our initial input X. And the log is now of the joint probability of all of these, all the latents along with our data as over the posterior of all the latents given our data point, right? Now, the reason why we dove all the way through to Markovian hierarchical variational autoencoders is because diffusion models are actually nothing but MHVAEs just with 3 additional restrictions. First of all, our latent dimension is the same as the data dimension. Now, the way you want to reason about it is, in general, you would have seen all of these diffusion models, web apps online working with images, right? And at each step, they would give you a different image. So of course, every single output should be the same size as the input, which is the same size as the image, right? So our latent dimension is now restricted to be the same as the data dimension. Okay. Secondly, the encoder here has no parameters. There is no learning of the encoder that happens. We know it exactly, and it is tractably calculable, and it is defined to be a linear Gaussian. What that means is throughout our hierarchical process, going from Z1 all the way to Z capital T, each Tth output is a Gaussian, which is centered around the output of the previous latent. So the mean is sort of a scaled version of what comes out of the latent right before. And our variance is predefined, and then we'll get to what these definitions are. Lastly, the parameters of the Gaussians that we are talking about here are scheduled such that the final latent is a standard Gaussian, an isotropic Gaussian, so that by the end of the process, we have no information left, right? It's complete Gaussian noise. Now, interestingly, the first restriction is only there in this lecture so that we can perform sort of some mild abuse of notation. What that means is we can completely get rid of all the z's there and talk about only in terms of x's because everything is the same size. It's just a different version of our data. So our posterior, which is x1 through t given x0, here you should know that x0 is our original image and xt is the final latent, becomes a joint product of all the individual posteriors of xt given xt minus 1. And our joint probability, now instead of having z there, becomes p of x0 through t times the only thing that stays out of this product now is our initial prior on the final, right? And once again, our phi and theta here are the parameters that we were initially learning in our VAE. So these are all of the little encoders. These are all of the little decoders. This is what it looks like. All we did was change all the z's to x's here, and it's essentially the same MHVAE with, as I said, the abuse notation. Okay, now coming to the forward-looking process or the diffusion process, and the second restriction is what helps us define it. So we define it to be a linear Gaussian for the encoding, right? What that means is every single qxt given xt minus 1, which is the latent for every state, is defined as a sampling from a Gaussian centered at mu t, which is a function of the previous latent and a defined variance. Here, mu t is defined. We define variables beta t, which is the square root of 1 minus beta t times xt minus 1. Here, this is the term that is scaling the previous output, and our variance is defined to be beta t as well. Additionally, we would also define alpha t, which is 1 minus beta t here. The only reason we do this is, once again, for notational ease. And the way beta t is defined, or it's scheduled throughout the entire process, is also to preserve variance across the diffusion steps. Essentially, you'll come to see that what we're doing is we're adding some amount of Gaussian noise to our input at every single step. And if we don't actually explode, right? So we want to preserve the variance throughout the process. Right, so we can now write our qxt given xt minus 1 as now being sampled from the mean, which is defined here as square root of alpha t xt minus 1, and the variance being 1 minus alpha t. All we've done is we've replaced 1 minus beta t with alpha t here. Cool. Once again, using the reparametrization trick, we can write, instead of the sampling, we can say xt is the mean, which is root alpha t xt minus 1, plus the standard deviation, not the variance, mind you. So it becomes the square root of 1 minus alpha t times a noise term, which is now sampled from a standard Gaussian, right? And here, if you try to expand this further, you use this sort of recursive definition of xt and open xt minus 1, you will arrive at an equation which looks like this. So xt can now be defined in terms of xt minus 2. And further, it can be defined in terms of xt minus 3. And so on and so forth till we reach our initial x0. to do this, if you try to do this by yourself, you realize that when you open it, expanding into the first term is very trivial, and arriving at the second term seems very, very difficult, right? Why would this happen? To sort of save you from that pain, the reason why it happens is the sum of two Gaussians is another Gaussian, with the mean as the sum of the means and variance as the sum of the variances. And this matters because you can simply use the second term here or the second term here to be a Gaussian, which has zero mean and has 1 minus alpha t invariance. So then we will add the two Gaussians, which will result out of u expanding xt minus 1, and you will arrive at the second term. Now, the math aside, the reason why we do this, or the reason why this helps, is we can then define another sort of accumulated term, which is alpha t bar, which is just the product of all the alphas up to now. Very simply jump from time step 0 to any time step t. We will know all of the individual steps to get to time step t. And you'll see eventually when we reach the training and sampling stage, this is immensely helpful, and this makes our process really fast. The third restriction, because we want to make our final sort of latent, the final step to always result in the standard Gaussian, we would want alpha t to reach 0. What that would do is it would collapse this product down to 0. So we have 0 mean, and it would collapse this down to 1. So it'll have 0 mean and identity variance. So it'll become an isotropic Gaussian. Right. With this, this formulation now essentially, of course, paints a picture of, right. It's a little bit difficult keeping track of chats as well. I'm just making sure that nobody's asking questions. Okay, cool. So this formulation essentially now paints a picture of this process to be incrementally adding noise till we reach xt. Why? Because we take a previous term, scale it, and then add some amount of noise to it, right? So we're essentially noising our input incrementally. So the diffusion process, which is this bottom row here, now corresponds to us taking our image or taking our sandcastle and destroying it ever so slowly, this time with Gaussian noise, till it reaches no information whatsoever. Right. Any questions so far? All right, great. We're doing amazing then. Okay, in case you have any questions in the middle, please shoot. Let me know. Please interrupt me. That's completely fine. I don't want to miss a question because it's there in the chat, although I will try to keep an eye on the chat as much as I can. Okay, so coming to the generative process. So now from the third assumption, in which we said that the final steps should reach an isotropic Gaussian, we can define the prior on the final step to simply be this sampling from this standard Gaussian, right? For all the other steps, we can then write a learned distribution, which goes in the opposite direction, which is from right to left in our previous diagram, to go from xt to xt minus 1 with a learned mean based on xt and time step and a fixed variance, right? This is parameterized by theta, which is why that's present here. And essentially, this mu theta is the output of our neural net. Typically, what we use is a U-net, which has denoising properties. I'm not sure. When I was taking the class, one of the quizzes had a U-net in it, very in-depth U-net questions. So I'm hoping you guys are slightly familiar with it. If not, no worries. It's not very, very pertinent to today's lecture. But all you need to remember is U-net has a bunch of blocks which are connected across its bottleneck. and it has residual connections, and sometimes they add in self-attention layers. All that does is it gives it very, very strong denoising properties. Essentially, you input a noisy data point, and it gives you a slightly less noisy version of it. Right, and our variance, of course, is defined, and it is exactly tractable. Cool. So now we can define the joint probability of our learned variables over theta to be basically the same thing. All we do is we put a little theta here, right? Cool. So with this, we can update our evidence lower bound once again. So we have our joint distribution, and of course we had our posterior as well, which we defined. Once again, the derivation is the appendix, which is to come. And we eventually reach an evidence lower bound, which looks like this. And this would make you sort of go, what? I have no idea what's going on here. This looks like a monstrous term. That is fine. We will deal with it. All these terms will decompose. But before that, we have a problem to address. If we simply go ahead and try to solve for this equation here, we will reach a point where we are trying to calculate expectancies over two random variables for every single time step. This is, well, considerably harder than using just one random variable. So why don't we try to find a way to do that? And interestingly, or rather superfluously, we can just arbitrarily modify the diffusion process to now also be conditioned on x0. So this is sort of given to us because of the Markovian property. We don't need to worry about that. But the only thing is, this is correct to state this. And if we use this statement here along with our derivation, we sort of arrive at a different but equivalent form of the evidence lower bound, right? Unfortunately, this equation still kind of makes you go, what is happening? But that's okay. We can deal with this monster now. So this essentially breaks down into three terms. And when you look at the terms individually, you will realize that the first two terms are exactly what we had in our original Elbo equation. So the first term here is the reconstruction, which is how well we can reconstruct our data point given the first or the least noisy version of our data. And this is a prior matching term, which is how close we can get the posterior, which is x capital T given xt, to our prior on that latent. If you set capital T to 1, or just replace that with z and replace x1 with z as well, because it's just a single stage, we would arrive at the plain vanilla VAE elbow, right? Which is where the equivalence of diffusion models with MHVAEs to VAEs comes from. And all that's left is this slightly longish term, which is called as the denoising term. Now, if you take a look at what it's doing, essentially, it is trying to bring this updated posterior as close as possible to the learned posterior, or the learned reverse diffusion process, right? Which is xt minus 1 given xt. Right, so in summary, the reconstruction term is the reconstruction from the least noisy version of the image. The prior matching term is trying to move the posterior closer to the true prior on the final noisy step. And the denoising is essentially the divergence between the approximate denoising and the true denoising Q steps, right? And out of all of these, the prior matching is set to 0, right? Because we know for a fact that the prior on the final step is a true Gaussian, and our denoising step is also a true Gaussian. So that is set to 0 because there is no difference between the two distributions. The first reconstruction term can be set to a very small, sort of almost constant value using the right hyperparameters. So what really ends up mattering in our loss term is the denoising term. So that's what we will end up focusing on going forward. The great part is this this true denoising term is not something we have to approximate or estimate the way we tend to do in machine learning. Here, term is exactly calculable, right? Completely tractable, exactly calculable, no approximations needed, no estimations needed. It is a Gaussian centered at mu t bar, and our sort of defined variance sigma t. And the mu t bar is defined by this slightly complicated looking equation. But the reason why it's very simple is we know all of these terms. None of these are unknown to us. Alphas are what we set. So most of this is given, right? Similarly for sigma, all of these terms are known to us. We can calculate it at any point with no problem whatsoever. Right, so now we can sort of have an alternate reverse diffusion process sort of set up above our actual diffusion process, sorry, the denoising process. And we can focus on the denoising term for our loss, right? Decomposing it for each time step, we can say that the tth loss term essentially is the KL divergence between the true denoising, which is xt minus 1 given xt and x0, and our learned denoising parameterized by theta, xt minus 1 given xt. Right, so since both of these are essentially Gaussians, and the KL divergence term has logarithms involved in it, what's exponentiated comes down and everything else goes into a constant c. So now all we're left with is essentially the L2 norm of the difference between the true mean of the denoising step at the t time and our learned mean of the denoising step, right? This considerably simplifies our loss equation. But we don't have to stop here. At this point, do remember that here our model is trying to output what a less noisy version of the data itself would be, right? Instead, what we can do is we can define, I mean, we already know that xt can be written in this form using the reparametrization trick, and we can write the true mean instead, use this definition to look like somewhat like this, right? So the mu t bar can be defined as 1 over root alpha t times xt minus 1 minus alpha t over 1 minus alpha t bar, right? This is only a rewriting of the mean itself. Okay. Now the predicted mean can also be rewritten to be of the same form. So it has all of the same terms here. All that's different is this noise term is now dependent on xt and t and parameterized by theta. And if you use this formulation, now all we're left with is the difference between the noises, right? And the reason why this is very, very powerful is that now our problem is no longer the problem of predicting image. It is in fact just predicting what is the noise here, right? What was the noise at the tth step on this latent? And once we know that, we can remove that from our image and immediately we have a less noisy version, right? Mathematically, these two are equivalent, but empirically, this formulation tends to work a lot better than trying to predict the whole image. Now, traditionally, you can also sort of look at this as essentially a scaling, right? This can be written as anything you want, like lambda t. And if you set that to 1 or completely ignore this term, it has also been found to improve the quality of the samples. But that's not too important today. Right, so once we are through with the diffusion process, the generative process, there's really nothing else left for us to do other than to actually train this model. And the way we do it, we start by sampling our data from our data set, which is x0 here. We sample a time step. We sample a noise from the standard Gaussian, and then we can immediately take the gradient descent step. If you're wondering what this term here is, you should recognize it to be xt, and we just repeat this process until our model has converged, right? The sampling process is also very simple. We sample, and for each time step, we figure out what that noise is. We predict the noise using this theta model, and then we subtract that noise from it. This equation is just presented by the inverse of what we had before. We add some variance to it. This variance is also defined, and we arrive at a less noisy version. At the end of this for loop, we would have our image. Unfortunately, at this point, there is no shortcut to go from x capital T to x0, the way we have it from x0 to any xt. But this is still fine. The training process is rather fast now than what it would have been. And the sampling process is easier. One thing that we did not talk about here is how do we tell the model what time it is? Basically, what time step are we on, right? We can't just input a random number. Well, I guess you could, but what we end up using is temporal encodings, which is very, very similar to positional encodings that you learned in transformers, in self-attention. It's basically a form of sinusoids. You can use anything, really anything would work, but empirically, this has been found to work the best. And right, with that, we are basically done with diffusion models. They are not such a large mystery anymore. As long as you know what VAEs do, you are 90% of the way there to understanding what diffusion models do, right? So in summary, diffusion models are just Markovian hierarchical VAEs with some extra restrictions. The loss is the vanilla VAE elbow loss with an added denoising term. The encoder has no parameters. There is no learning of the encoder. It is defined. The true denoising posterior is also exactly calculated. The problem can be reformulated as a noise prediction problem. And also there's a ton of math which I swept under the rug underlying this rather simple intuition. The reason why there's a lot of math is I don't know if I mentioned is this sort of concept is borrowed from statistical physics. So there's a lot of diffusion mechanics of gaseous fluids, which sort of ended up being the inspiration to this, which is why we chose not to dive very, very deep into sort of the core mathematics of this. But as long as you develop this intuition that it just builds on top of VAEs and then it's VAEs on top of VAEs with some restrictions, we're all good. Right. So any Okay, cool. Well, some of the very popular diffusion models that you would have heard of are things like DALL-E, DALL-E 2. Adobe now has a ton of diffusion models baked in. As I mentioned, there's a company called Runway ML, which make very, very cool videos about what they do, which is primarily why I know about them. They play around with diffusion models a lot and create some very exciting models. So yeah, and most of the text to image generation that you see out there now is also based on diffusion models. All that does is it plugs in sort of a multimodal version of this diffusion process. It finds out how to encode text into the same dimensionality or in a common dimension for text and image embeddings, and then we can go from there to generate images, right? Intuitively, there is no complicated processing happening there. Right. With this, we can move on to the second part of the lecture, which is normalizing flows. Right. So for a minute, let's go back to our Sandcastle example. And here I mentioned that you can also approximately remember how you destroyed the sandcastle, right? Which is what we did in the diffusion process. We learned how to go back through the diffusion steps, right? Now, what if we wanted to do this exactly? What if we could remember exactly what we did and we could exactly revert to our initial sandcastle from the destroyed version, right? So in VAEs, we are faced with an intractable likelihood calculation, and then we use the elbow instead as a surrogate objective to MLE, right? We want to do maximum likelihood estimation, but instead we try to maximize the lower bound on it. But as I said, what if you want to do maximum likelihood estimation exactly or directly? Well, what that would require is for us to go from the sandcastle to sand and back to a sandcastle without any approximations or estimations, right? And this naturally means, well, if we sort of think not in terms of sandcastles here, but in terms of probability distributions, and this is my beautiful hand drawing here. On the left, Here we have a slightly complex probability distribution, and we have these 8 points on it. We destroy it, we normalize it to be a standard Gaussian, and we map all of these points on it, right? And we want to go back. So we want to maintain this mapping of one point on the left in X to the point in the latent Z, right? For that to happen, well, the function G or the function F, both of them need to be bijective. And why? Because we want an invertibility. We want invertibility because we want to go from X to Z and Z to X with no problems and exactly. Right. So, of course, this follows that the two functions that we defined here, F and G, G being the normalizing function, F being the regenerative function, are inverses of each other. So G is essentially F inverse, right? The way this is different from VAEs also is that they typically have a bottleneck in the middle, right? So tends to be smaller than our input dimension. And that naturally means that there can be more inputs than there can be latent dimensions. So there will not be any bijectivity. In fact, there will be surjectivity. So there won't be a one-to-one mapping, but a many-to-one mapping, which is, of course, not invertible. Right? But in this case, if we actually define a function which is invertible, this is entirely possible. Okay, so the log likelihood, the bijectivity or the invertibility allows us to compute the log likelihood directly using just this sort of probability mass preservation equation. And we reach a point where we can write that the log likelihood of X is the log likelihood of Z, which is defined by G of X here, plus the log determinant of the Jacobian of G of X. If you notice this step here, the reason why this Jacobian shows up is in multiple dimensions, this partial differential turns into the determinant of the Jacobian. And what this means is intuitively, this G mapping determines where a point in this X space maps to Z space. And this determinant of the Jacobian of this mapping tells how much the probability mass or the sand is squeezed and shoved aside in local neighborhoods. So around this point X, how much would it be moved around so that this is transformed to this point here? Right, we can also arrive at this final equation through what's called as, well, the change of variables formula in probabilities. If you know about that, that's great. I just didn't want to throw a term around. The way we reach it is simply by expanding on this integral. Right. Something I do want us to take a closer look at, once again, in my beautiful hand drawing, because I couldn't get to make this on PowerPoint, is what the Jacobian looks like. So now the Jacobian of Gx with respect to X is this matrix here, in which we have the partial of Z1, which is the first element in Z, with respect to X1. At the end of this row is dZ1 given dxk, k being the dimensionality. At the bottom here, we have dzk given dx1, and on the rightmost here, we have dzk over dxk. The reason why we are taking a look at this is because this will become important when we finally formulate our normalizing flow. But as long as we keep this picture in mind, we should be good to go. Right? So it's just a matrix in which every single element is a partial differential of one term of the input and one term of what is actually what we are differentiating with respect to. Okay. So what bijections also allow us to do is composing several functions together. I mean, functions can always be composed, but now we can compose invertible functions. Well, ft of ft minus 1 all the way till f1 of z can be inverted to get z back, because all of these functions are invertible, right? So instead of going from x to z in one step, instead we take a few steps to go back and forth, right? And now this picture is starting to look a lot like diffusion models, right? In essence or intuitively, they are kind of doing a very similar thing. They go from sort of a complex distribution and they try to in diffusion models, we try to add as much noise as we can to reach a standard Gaussian. Here, we are actually mapping the points one by one so that eventually, after all of these transformations, all the points are mapped on top of a standard Gaussian. Right? That's the key difference here. So the great part is that because all of these are invertible and this is basically a composition, using a combination of the chain rule for composed functions in differentiation, along with the fact that determinant of A times B is the determinant of A times the determinant of B. And once you take the log of products, we get a sum. We reach a log likelihood term, which looks like this term here. Right. And once again, we do a slight abuse in notation. ZT is defined to be X, which is the end of this process here. And Z0 is Z, which is the beginning of our latent to complex journey. Right. And as I mentioned, we can always go the inverse way. So Z can now be equal to Z G1 all the way to GT of X, which is our initial data. Right. So normalizing flows, for a good flow, we need to have a few characteristics here, right? Each of the functions need to have these characteristics. One, they need to be expressive. Two, they need to be invertible, of course, because otherwise we can't go back and forth with ease. And third, they need to offer cheap to compute Jacobians, right? Sorry, Jacobian determinants. Now, computing the determinant is a cubic operation, right? Because we keep taking submatrices, finding their products and multiplying it by a diagonal term, and so on and so forth. But there are some matrices which allow for this determinant calculation to be very, very cheap. Would anybody like to take a guess? I've been talking for a while. I'm kind of tired of my own voice now. Any guesses? What kind of matrix makes it very easy to compute determinants?
Like triangular, something like
Yeah,
that.
exactly. Yeah. So triangular matrices make it very, very simple, right? Because all you're left with is a bunch of zeros on one side that cancels out the remaining triangle, and you only need to make a product of the diagonal, right? Similarly, of course, a diagonal matrix is also, of course, a triangular matrix. So all we need to do is care about the diagonal terms. So if we can achieve a Jacobian where at least one triangle is all zeros, then the computation of this determinant of the Jacobian would be super simple. And here I decided to borrow Wikipedia to sort of define diagonal matrices in case somebody is confused. But what that means is you only have diagonal terms. Nothing else is non-zero. Okay. Cool. So now I would like for you to follow this construction of the function f here. Now this construction is, of course, borrowed from existing architectures. This is what's called as a coupling flow architecture. We don't need to dive into all of that. But if our requirements. Okay, so we take our input data, x, which has a bunch of terms. We split this into two parts, right? We take x1 and x2, which goes from the 0th element all the way to some small d element. And this one goes from d plus 1 all the way to k, right? So we have x1 and x2, and we can arbitrarily split it anywhere. Nothing to it, and we place it in the first half of our latent, which is z. We then take the same x1, we pass it through a neural net, and then the neural net gives us two, or A and B, or M and S, whatever you want to call it. And what we do with these two values is we apply these two to make an affine transform on x2 to arrive at z2 as alpha x2 plus beta, and then we place it right under z1. right? And then all we do is concatenate them, and then we have Z, right? Well, first of all, we would like to see that, is this function, this weird function here, is this invertible or not? Well, any takers? Do you think this function is invertible? Going all the way from X to Z. Oh, that's right. I can actually do a poll. Well, I'd rather not experiment with Zoom. So let's do a poll on the chat itself. How many think that this is invertible? Okay, a bunch of yeses. Does anybody think it's not invertible? Okay, I see semi-invertible there. Would someone like to explain why they think this is invertible? Actually, if I can borrow a page out of Professor's book. Muhammad, you mentioned that it is semi-invertible. Could you explain what you said there? Why do you think it's semi-invertible?
Because it's using the neural network, which is an approximation.
Correct. So you're saying that this network itself cannot be inverted, right?
Yep.
Okay, but what about the rest of it? Do you think we can go from Z to X without having to worry about the neural network here?
Partially, because you used half of the data.
Okay. That's fair. That's completely fair. So the neural network itself cannot be inverted, but something that we want to keep in mind here is typically all neural networks in practice are deterministic, right? So since X1 and Z1 are the same, essentially, no matter which one we feed into the neural net, we will always get alpha and beta, right? So going backwards, we can start with Z. We can split it up into Z1 and Z2 at the same point as X. We can place Z1 as it is in place of X1. We can pass Z1 through the neural net, achieve the same alpha and beta as X1 would have given us. Then we can take Z2 and apply the reverse affine transform, which is, we can say X2 equals Z2 minus beta over Z2 at where X2 is, right? After the transform. So even though, as you mentioned, the neural network is not invertible, we don't need to invert the neural network here, because we can go from Z to X given a deterministic setting for the neural network to not cause any problems. What's more important here for us to look at is how this helps us formulate the Jacobian, right? If you remember the big picture for the Jacobian, each of these little terms is how Z1 changes with each X1, right? Now we know that this split here, which is corresponding to these splits here, X1 and Z1 are the same. The only thing that's here is an identity transform. So the way Z1 changes with X1 is just identity, right? These are ones all the way in this little submatrix is diagonal, and everything else is 0. Cool. Z1 has nothing to do with X2, so it changes. So all the terms here would be 0, right? There is no relation whatsoever. Z2 does in fact change with X1 in a complicated fashion because there is this neural network here which needs to be differentiated. But we can ignore that for now and focus on this bottom right, which is Z2 with respect to X2, and all that's there is a diagonal of alphas, right? Because all these terms are scaled. If we differentiate this with respect to X2, we will only get the alphas. Now, what's great is we can completely ignore this bottom left square here, which is supposed to be the most complicated part, because all of its counterparts are zeros, right? So when we calculate the determinant here, there will be some ones and a bunch of these alphas being multiplied. And in log terms, they would just be added together, right? So this is great. we that's okay. We were able to satisfy invertibility. We were able to satisfy offering cheap to compute Jacobians. The way we satisfy expressiveness is in two parts. One, we do it by having several stages, right? So that we can incrementally apply transformations so that we can destroy our given distribution to reach the normal distribution. The second way we do it is by giving depth to this neural network here for it to be able to capture more and more sort of complexity in the data, right? Now, going off of that, we can chain all of these together to now be the different stages of our flow, right? This will define the normalizing flow. This is wonderful, but there is a small problem here. Can anybody spot a problem with this flow? To try to spot it, think about what's happening to our input as it goes through all of these stages.
Maybe one part of X remains the same throughout.
Exactly. Also, that was funny. The subtitles thought you said eggs instead of X. But anyway, indeed, some of the part of the input always stays the same. It's like it's on this express highway from the input X to the final output Z. It's not changing. So we need to employ a sort of permutation here, right? What we can do is we can insert a shuffle or permutation layer to go from the concatenated version to the Z. Now, you would maybe think that this would spoil our semi-invertibility, but in fact, it doesn't. A shuffle is nothing but a linear transform. We simply multiply this vector with another matrix, which is a shuffled version of the identity matrix. We just shuffle things around. All we need to do is remember what we did, and then we can trivially invert it, right? We just multiply Z with the inverse of that matrix, and then we will arrive back at our invertible, semi-invertible stage, right? So this is what's known as, well, the most popular type of flow called as coupling flow, which is used in implementations, popular normalizing flow in implementations like NICE and GLOW. There are a few more which employ a not so easy to calculate determinant of the Jacobian. But even though they're slightly more complicated, these have been found to work the best, right? So now, instead of simply chaining a bunch of these blocks, we insert shuffling blocks, and then we chain those together, and then we have our flow. Reversing that, we have a generative process. So now we have a great way to go from X all the way to a completely normalized version or destroyed version of X in Z, and then go all the way back to reach X. Right. So in practice, when we do it for images, we use a multi-scale architecture. What that means is instead of you having just a single affine scaling step here, we also scale the other half, but in a separate stage, so that at least in one step, only one of them is transformed, right? We split along channels instead of splitting along the vector's dimensions. We employ CNNs for the network. You can really use anything. You can use an RNN if you want, but CNNs tend to work well. And you perform the permutations using 1x1 convolutional layers. Once you employ all of these four characteristics, you arrive at GLOW, the paper which largely produces the best results for normalizing flows. And this is what those look like, right? These are really great. If you take my opinion, I would say a lot of their facial features are very similar. Perhaps changing the temperature value would change how different the faces look. But in general, the images are of very high quality. What was interesting is they were also able to train it to do other than just image generation. They were able to use it to make image transformations, to go from images on the left to images on the right. And yeah, with that, we are at the end of normalizing flows as well. I tried as high level as possible. The idea here was never to completely understand the math, but sort of gain an intuition about how both of these networks are working. Diffusion models are arguably a lot more popular at this point for in terms of generative modeling, but normalizing flows are interesting to know because they kind of follow a similar intuition with a more exact formulation instead of approximation. Right? So my fault for not having a summary slide here, but something to remember or how these two differ is this slide here, right? In VAEs, diffusion models, HVAEs, MHVAEs, all sorts of variational inferences using VAEs, we always have an approximation. We have a surrogate to the MLE, which is done by maximizing the elbow. Normalizing flows instead using invertibility and invertible functions, we are able to exactly the way we do the maximum likelihood estimation is by using this log likelihood function. All we do is maximize this term, right? And the great part is this determinant is very easy to calculate because it essentially becomes a sum of determinants. And yeah, so with this, we have two new forms of generative models in addition to things like transformers, variational autoencoders, eventually, I believe, GANs. I'm not sure if the GAN lectures are still included. I'm guessing they are. So they sort of form this landscape of generative models. I believe we are early today. Oh, actually, we're only early by 7 minutes, so not sure on that. But at the end of at least the slide deck, which I provided the TAs right now, there are a bunch of references. I had to go through all of these to sort of make this lecture, remove some details, but these are all amazing papers. Particularly, I would suggest that you go through this paper here. It seems like a 50-page explanation, but it's really 10 to 12 pages of diffusion model explanation. It goes all the way from variational inference all the way to diffusion models and sort of an interpretation of diffusion models as score-based models as well. So this is a very, very good paper. All the papers on normalizing flows are actually surprisingly easy to understand. They don't use very many heavy terms, simply because I think all the building blocks are pretty simple, right? In addition, there are 3 lectures which I watched, particularly the Sandcastle example. As much as I would like to take credit, it was Hans van Gorp's little lecture. This guy is a very less known YouTuber. He has like 79 subscribers. I was, I think, the 79th subscriber once I saw this lecture. But it was a brilliant, brilliant example. I tried to come up with something different. I decided not to because it's better not to touch something that's already great. Right. And in addition, this is Tim Salmon's lecture on diffusion models and variational autoencoders. And this is Dedrick Nielsen's lecture on, normalizing flows and diffusion models. The only thing that's different here is they like to go through their work, which is on text instead of images as well. So if you're interested, feel free to watch those. But yeah. Any questions for the remaining 5 minutes? I will stay on call and answer any questions that may exist.
I have one question. When you go from the process of moving from noise to the original image, what the model produces, must it be an exact image of what was input, or it must look similar to it? Let's say, for instance, if the original image was a cat and then it's not, it's, can you say noise it? It noises it, and then you denoise it. Does it get a higher accuracy if it gives that same cut, or it does not even matter? I don't know if the question is clear.
I think I kind of understand your question. It's essentially getting at what is the model doing, right? So I will just continue to take the Sandcastle example. If you provide the tth step with this image, it would, so depending on which formulation you're using, assuming you're using the noise prediction formulation, it would essentially predict a similar sized version of what it thinks is the noise, in the image. And then our sampling process, generation process would remove that, would subtract that from it. So say we have an image at time step t, which is xt, which we feed into the t time step. We receive a noise from the input, which is epsilon theta, and then we subtract the epsilon theta from xt to get xt minus 1. And then the same process carries on. Does that sort of answer your question?
So let's take, for instance, this the original, or once it denoises and it arrives at this original, maybe for instance the blue in it is missing. Does that mean it's a higher loss? Yeah.
Oh, higher loss. Oh, I see. So during the training procedure, let's get to that slide. If you get to the training procedure, here the reconstruction is measured between what's constructed from the least noisy version of our generation process to the final image. And then it measures it against the true denoising process, which is Q x1 given x0, right? It takes an expectation over that. So it wants to maximize the likelihood of the data that you gave it. So if the image that you produced does not look like the image that you gave in, this is the term which would increase the loss, right? Per time step, if you are not denoising properly, all of these t-2 terms are what will contribute to the loss, right? And in case, this will never happen. This will always be 0. So we can sort of ignore this entirely.
Thank you.
Mm-hmm. Something that I did not mention is how many time steps we go through. The original diffusion paper, which actually came out in 2015, and no work was done on it until 2020, I believe, when the same authors released an update to the diffusion process, making it a denoising architecture instead. Was initially they used 1,000 time steps. And the 1,000 time steps is only done so that they can completely ensure that the final version is a Gaussian, right? So the way you would ensure that it's a Gaussian is by taking enough steps. However, there is a flip side to that. We don't want to go too far so that the last few steps offer no information whatsoever. If we have already reached a maximum noisy state at, say, step 900, we don't, with just adding noise on top of noise, that will provide no information to the model whatsoever, right? So we try to choose a number along with our formulation so that at the end, at the last time step, we are guaranteed Gaussian noise, and that is the minimum that we need to do.
All right, everybody, I'd really like to thank Abu over here. This was a fantastic lecture. And if you have any questions, please post on Piazza, and you can always ping Abu. He knows the stuff, obviously. And Abu, thanks.
My
Just
pleasure.
as good as I expected it.
My pleasure. I was a little nervous because these topics are slightly new to me as well.